If not, then you can always like post your questions or directly email me if you have any questions regarding regarding all these metrics. So let's move into the next section, which is the dialogue level metrics. So the difference between dialogue level metrics and the turn level metrics that we look at is kind of global versus local thing. So we look at in global level, the multi-turn, the quality of the dialogue instead of a single turn, like only the quality of the single response. So that's a difference. So the first example of this category is the FED. Actually, FED is tailored to both turn level and the dialogue level evaluation, but it is kind of the first to introduce a reference-free metrics specifically for the dialogue level. So it's published in SIGDial 2020, and so basically the motivation of doing dialogue evaluation is that some of the erroneous behaviors can only be captured after observing the entire dialogue. For example, consistency. Only after we interact with the chatbot for several turns, then we can notice that whether the information the chatbot conveyed now is whether it contradicts what it says before. So sometimes if the chatbot may tell you I'm happy, then after continuously interact with it for several turns, you ask him how are you feeling, or it says I'm sad. So it's kind of contradictory. So we want to capture such kind of erroneous behavior. So of course, for both turn level and dialogue level, they have a different set of quality dimensions, meaning that both have a fine-grained dimension instead of only in the overall overall quality. So we look at different dimensions. And most existing metrics and evaluation data sets are about turn level evaluation. So dialogue level evaluation is only like gain attention in recent 2 years, starting 2021. So this FED targets the multidimensional evaluation at both turn level and dialogue level, and introduce the data sets and also a FED matrix. So I will go into the FED data sets. So first, this same group of researchers from CMU, they annotate this they collect dialogues, like interaction between human and the state of the art dialogue from Google or human conversation. They try to annotate the interaction both at the turn level and dialogue level. So at turn level, they are like 9 different dimensions they annotated. Here is the score range. 1 indicates, for example, the response is not interesting. 3 indicates it's very interesting. So that's the annotation at the turn level. So our focus is at the dialogue level. So the dialogue level, they annotate along 11 different fine-grained dimensions. So basically, one is the coherence. So globally, whether the system is coherent and maintain a good conversational flow. So 1 means not coherent, 3 means very coherent. So they are like 11 fine-grained dimensions. And this FED data sets, basically we mentioned just now, so it's annotated. There are 125 dialogues that come from 41 come from the Human Mina, which is a Google chatbot interaction, Human Me True School, and the human conversations. So there are 125 dialogues that are annotated. So for each dialogue, 3 system responses were hand selected to be annotated at the turn level. So there will be 375 annotated response, and also each dialogue, each data instance is annotated by 5 crowdsourced workers. And we can observe that actually the inter-annotator agreement are quite high for all the dimensions. So most of them are above 0.7. This means that the quality of this data set is very good because the humans are all agreeing with each other. So when we do develop metrics, we want to optimize our correlation with human correlation as high as possible. So this column here kind of serves as the upper bound of the metric performance. So after they construct the FED data sets, they also introduce this FED metric. So basically, the FED matrix is used the follow-up evaluation to evaluate the current response. This means that a unique advantage of dialogue is that we can always check how well we are performed based on the reaction of the other party, means the person we are chatting with. So that's why this matrix leverages such advantage. So they collect a list of for each dimension, such as interesting. They collect a list of positive follow-up, like for example, I say something, I want to tell whether what I say is interesting. Then I check whether the other party by reacting like, wow, that's very interesting, or the other party say something like, that's not very interesting. So we want to see the probability of generating such follow-up utterances conditioning on what the previous context and what I say just now. So it's kind of intuitive. This metric is kind of intuitive. So the author relies on the pre-trained dialogue GPT model, a large language dialogue specific language model, to predict this kind of conditional likelihood. Then they use here the P here is a set of positive follow-up, N is the set of negative follow-up. So if the probability of generating positive follow-up is greater than the probability of generating negative follow-up, then it means that what I say is interesting. Then otherwise is not interesting. So that's the main idea behind this metric. Sorry. So let's check the performance of FED. So because this is a fairly new data set, there is not many prior work baselines. So they also try to compare the proposed, use different variants of the dialogue GPT model to do the comparison. So actually, because compared to the human upper bound we see just now, some are like 0.8, some are like 0.7. The performance of the FED is kind of fair for both 10-level evaluation and dialogue evaluation, especially for the overall dialogue level evaluation, is 0.4, which is kind of good enough, but there are still like room for improvement. So next, after FED, then in 2021 A0, actually we proposed this DynoEval framework to try to evaluate the dialogue level coherence. So it's specifically targeting the global coherence of the dialogue. So basically because dialogue can be seen as a multi-turn interactive process between the speakers. So there are two aspects that are kind of essential to this interactive process. One is the speaker level dependency, which means that the relationship between the speakers, like the ordering of speaking. And the second is the utterance level dependency, which is the semantic relationship between different utterance pairs. So these are two types of relationship. And in the paper, we try to adopt a acyclic direct graph to model such a hierarchical structure. It's kind of intuitive way to study and to model these two types of relationships. So here is the architecture of the DynoEval metric. I will not go into every tiny details of the model. So basically, I will just roughly tell each module what each module does. So for this S-Robota is basically a Robota model that try to encode the utterance into the corresponding sentence vector. This D here is the original dialogue, like human multi-turn dialogue. The D bar here is like we perturb the dialogue, like we randomly replace some utterances so as to create some sort of negative samples. Then after that, they are fed into the LSTM. So after the S-Robota, then their embedding vector are fed into the LSTM. So this is to capture the sequential flow of the utterance. For example, this utterance from speaker A, from speaker B, and from speaker A again. So it's a kind of sequential, want to capture the sequential context. Then after that, we use the LSTM output as the node embedding initialization for graph construction. Then here, so here we try to connect the relation, the age is kind of try to model the relationship, the speaker level relationship and the utterance level relationship. So we use another GCN to like kind of do the feature transformation from the original node embedding to a kind of a different set of embedding which captures which aggregate the information from the connected labels. Then after that, we want to, because for each dialog we want to obtain a single representation, so we adopt some sort of pooling layer, min pooling or max pooling. We can obtain a single vector for each dialog. So after that, after a fully connected layer and a sigmoid function, we can obtain a single score for both D and D bar. Then we use the margin ranking loss to train the model. Yeah, so here is the margin ranking loss. So if the label is 1, so means that D is preferred over D bar. Label is -1, then D bar is preferred over D. And because, so here is two sampling strategies we use to obtain the negative sample. One is utterance replacement, the other is utterance level shuffling. So this one is perturb the semantic, and the speaker level utterance shuffling is to like change the order of the utterance. So it's to manipulate the coherence. And the training data sets are the commonly 3 data sets we introduced already. So this conv-AI2 is basically a larger set of personal chat. So here is some, the right is some statistics of the dialogues. And if we look at the performance, the first task we want to see is the binary classification. So we want to see whether DynoEval is able to tell coherent dialogue from incoherent dialogue. So we can see that compared to baselines, it's actually performed quite well in discriminating the coherent dialogue against the negative ones we generate with this utterance replacement and speaker level shuffling strategies for both all the 3 data sets. Then we look at the correlation of the DynoEval. So compared to FED, FED we introduced previously. So in terms of coherence, dialogue level coherence performs significantly better, as well as the overall quality. So based on the result here, we can see also that DynoEval and FED is kind of complementary of each other, because because FED is specifically tailored for, they have a different set of follow-up utterance for different aspects, so they can capture a different quality fair enough. But DynoEval is only like designed for coherence evaluation, so it's not very good at dimensions such as diversity and on something like understanding. So they are kind of complementing each other. If we combine them there, they may perform better. But we can see that their performance is still far from the human upper bound. So there are still room for improvement. So the second last matrix I'm going to introduce is DEEM, which DEEM is an improvement of DynoEval. Basically, they criticize that the previous methods such as DynoEval only rely on like text level heuristic perturbation strategies. So this type of manipulation may be insufficient to reflect errors in more advanced dialogue systems, such as the recent BlenderBot, so on and so forth. So they try to apply the abstract meaning representation for semantic perturbation, such as co-reference inconsistency, irrelevancy, contradiction, and decreased engagement. These 4 types of semantic level perturbation. Then here is basically the detail of the metric. So basically they adopt a Robota model and a classifier on top. So it's a classification, sequence classification based Robota, but they try to classify the original dialogue here and the the ARM-based perturbed dialog. So they first try to convert the original dialog into ARM-based representation, then do some manipulation according to the some manipulation specific to each perturbation. Then after that, adopt the pre-trained ARM to text generation model to reconstruct the dialogue. So they try to discriminate this one, the original one, with the generated dialogue. So that's a basic architecture of DIM. Then here is basically some example of the ARM representation of the conversation. So and here we introduce the steps, the flow of the flow of the generation. First is to use the pre-trained ARM parsing model to translate the conversational text into directed and acyclic ARM graph. So this ARM graph is basically a logical representation of the semantics of the sentence. And then the graph also contains the relation age between the entities, or something like the relationship between you and the Sesame Street, something like that. Then after that, they will perform some specific manipulation on the ARM graph. Then after that, they adopt a pre-trained ARM to text generation model to convert the perturbed graph back into the conversational text. So here is the details of the each perturbation strategy, the irrelevancy, co-reference, inconsistency, decreased engagement, and contradiction. Due to time constraint, I will just introduce one. So for example, after passing Have You Watched Sesame Street into the ARM representation, we have the node, the watch, then they kind of like perturb this node to like listen. So it's like kind of change the graph structure. Then after that, they generate this perturbed ARM structure back to the text form, like it becomes you listen to Sesame Street. So it's kind of still it's a kind of adversarial sample. So after we change Have You Watched Sesame Street to you listen to Sesame Street. So basically that's more advanced way of perturbing the text. So in terms of performance, we can see that here the correlation compared to both DynaEval on the FED dataset, in terms of coherence and overall quality, the DIM model actually achieved significant improvement. So the final matrix I would like to introduce is a FindEval model, which is published in EMOP 2022. So we observe that the correlation of DIM and DynaEval with human evaluation is still not very strong. A major reason is that their perturbation strategy only targets dialogue coherence. If you recall previously, we mentioned that dialogue level, there are many fine-grained qualities, but these two existing metrics, they only target dialogue coherence. So we should consider more some metrics to model those fine-grained dimensions. So this paper, fine-grained automatic dialogue level evaluation, targets such multi-dimensional evaluation to the dialogue level. So the categorization of dimensions based on the FED data set, we can see that they introduce 11 fine-grained dimensions, but some dimensions are quite correlated. I mean, are similar to some dimensions. Some are quite different from each other. So we don't want 11 fine-grained different dimension matrix for each dimension. So we want to like metric for one group of them. So we try to do some analysis to cluster this 10 fine-grained dimension plus the overall, okay, into different groups, like different clusters. So the clustering is basically based on the correlation of human score of different fine-grained dimensions with the pairwise with each other. For example, the coherence and the understanding, they highly correlate with each other, like 0.8. So we can put them together. So similarly for other dimensions. So in the end, we obtain 6 groups. So in this paper, we just model the first 3. Then, so basically we for training the submetrics, we adopt a similar preference learning framework that we use to train DynaEvolve, but it's just we adopt different sampling strategies for different groups like coherence, likability, and the topical depth, and the submetrics are combined through ensemble and multitask learning. So for coherence, basically we adopt the utterance order shuffling and the QA relevance scoring technique. So the utterance order shuffling is basically random permute the order of the utterances in human-human dialogue. For the QA relevance, it's more pertaining to the understanding aspect. So if we try to adopt a pre-trained QA evaluator to score the QA pairs within dialogue, the higher the score, we think that the chatbot is kind of understanding the user. And if the lower the score, so it's kind of not understanding. So there's two strategies for coherence. Then for the likability, so we adopt another two strategy. One is contradiction scoring and the number of utterances that carry positive sentiment. For example, for this number of utterances carry positive sentiment. So the more utterances that are positive, we think that the dialogue is more likable. There are some the user feel the chatbot is more interesting. The lower number, then is less interesting. So also for similar for topic depth, we adopt this interment scoring technique to evaluate to model this dimension. So for example, we try to show that different utterance pairs, if they are semantically similar, we think that they are less information conveyed. If they are like more semantically different, like the interment score is lower, then the information may be higher. So in this way, we can train a submetrics pertaining to topical depth. Then lastly, we combine them through ensemble or multitask learning. Then we compare them with all the baselines. We can observe that this FindEvolve matrix, the combined matrix, perform well across all the fine-grained dimensions as well as the overall dimension. So it's significant boost above DIM and DynaEvolve. So that's all for my section. So sorry for taking too long. So do you have any questions? So, okay. So actually, if not, maybe you can like email me or like send private message to Luis and me if you have any questions on the reference-free matrix. So I'll pass on to Luis to wrap up the presentation.
Yes, okay. Let me try to finish quickly because we have only 5 minutes left. So basically, what are the challenges and future directions that we have? So as we have seen along the different parts of this tutorial, metrics are limited in scope. They have a limited set of dialogue qualities, dimensions, languages, culture. So those kind of things we are not really focusing right now, but those are interesting dimensions that should be included in future metrics. Also, they struggle to generalize. For instance, if you change the sentence, the wordings, then the system will generate a different score that with the original sentence. So systems or metrics should be robust against these semantic variabilities on the sentences. Also, they sometimes are not strongly correlated with human judgment, especially when we are talking about real users. For instance, in the Alexa Prize last year, we tried to use one of our metrics into the Alexa Prize scores given by the users. What happened here? And then we couldn't get really good results from humans. Let me share the screen again. Okay, so there are also inconsistencies between data sets, and that's made difficult also for this dimension. So there is one claim that we also need to mention here is the need for data sets that include different, that are clearly unifying the definition and terminology of the dimensions to be evaluated. We have found data sets that contains two different or different names for the same dimensions, and this makes it difficult to use them because each one is targeting the same dimension but with a different name. Then other data sets do not cover different new dimensions like toxicity, bias, coherence, hallucinations, common sense usage. All these things are required in order to provide improvements over these data sets, metrics. Then we have also fine-grained annotations. Sometimes we have only dialog level annotations, other times we have turn level annotations. But what about long-term interaction? Do we have annotations for those? Basically, no many data sets or no data sets almost at all for covering all these different dimensions, right? Then we have seen that in other topics, in other fields like MT, Q&A, NLG, there has been a lot of progress because there are benchmarkings, because there are data sets. So we have been also with Chen and different researchers around the world, we have been working on creating this kind of benchmarkings, these data sets. We gave you here the links so you can go and check, because if you're interested in working on this topic, then definitely there are resources for this. Then what we are looking for is some of the desired properties for metrics, a strong correlation with human judgment, interpretability, as I said before, robustness against adversarial attacks. We want also to have metrics that are generalizable across different domains and dimensions that can be used for forward and backward looking. Sometimes we have only that metrics that only look backwards, but they cannot see what is going to happen or predict what is going to happen, because I say this response from the chatbot, this may create completely or break completely the dialogue. So this kind of metrics, checking what is the effect of this term into the dialogue is also important. And finally, we also want datasets that are compatible with human evaluation. So human can be in the loop for error correction. So if you are interested on more datasets or new datasets, please check these links that we are providing here. We have been working with different researchers to work on this, to create repositories with datasets so people can go use them and check the performance of their metrics. We are also running different evaluation benchmarkings like the ones that we have during DSTC 10. So here you can see a long list of datasets that we use, we provide to the participants. It doesn't mean that we created all these datasets, but it means that we put them in a format that is easier for everyone to go and use their own metrics on these datasets. So this makes easier for people to evaluate their own models. We are currently running DSTC 11, especially the track 4. If you are interested, you can go to these two links, GitHub or Chatibal. We are releasing new datasets also for multilinguality evaluation, also for robustness. So you can see here basically the schedule of this track. At this point, we are running the track. We are releasing training and validation data, and we are planning to release the test data for around March. So if you are interested, please go to these links or check for DSTC 11 track 4, and you will get more information. Here you can see the people that we are working on this, including people from Tencent as well, and other companies. So what are our conclusions? Automatic evaluation is something very important to improve the performance of dialogue systems, because this will reduce costs and speed up deployment. We have seen different types of metrics: action level, dialogue level, reference-based, reference-free, train, untrained. So we have a lot of things, but it doesn't mean that it's done. There are many, many other situations that we are required, like new dimensions, robustness, languages, explainability. All these things are important to provide improvement, especially what I'm saying before, new data sets, new annotations, also schemas for sharing data, so everyone can share the data and make easier for people to understand the evaluations, the metrics, the people they selected for doing the evaluation, etc. If you need repositories, we have given here a list of few repositories where you can find data, benchmarkings, libraries for performing the references. Also, we provide overview of few papers that you can consider going deeper into the understanding of these metrics, so you can check any of them. And finally, if you really want to start working with current state-of-the-art approaches, then for dialogue level, I will recommend you to go and make a deeper understanding of FINE-EVAL. This was explained by Chen already. Is the state-of-the-art, the current state-of-the-art on dialogue level. And if you want to move into turn level, then I will recommend you MDD-EVAL. It's also the current state-of-the-art. For both of them, you will find in the paper the corresponding GitHub repository where you can find all the things, all the data. So it will be very easy for you to start working starting working with the LATs and the BETS versions of these current systems at this time. And okay, with this, we finish the tutorial. We hope that you enjoyed the tutorial. If you have any question or you have any request, you can send us an email and we will be happy to provide answers for your questions. If not, then we can finish here the tutorial. And we thank all the audience for being there and thank you for this opportunity of sharing with you what we are doing also in this area of metrics.
Yeah, thank you, everyone.
Thank you.
Okay, thank you.
We'll stop here.
Yeah, we can stop here. And I think the slides will be shared with the participants. So any question, just let us know. Okay. So
Okay, thank you.
thank you.
Thank you.
Bye-bye.
Bye.
Bye bye.